Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, I would like to continue going through Chapter 3.2 and look at systems of linear equations with infinite solutions. In our first video in Chapter 3.2, we began to look at systems of equations, and we introduced the Gauss-Jordan reduction method for solving systems of linear equations. In our first example, we looked at what a solution to a system of equations with one solution might look like. Graphically, we would interpret this as the intersection of three planes. And at the intersection, the ordered triple x, y, z, that would be the solution to our system. In today's video, I would like to explore another scenario when we might expect to see an infinite number of solutions to our system of equations. This could happen if our three planes intersect along a single line, or if our three planes actually coincide with each other. All three planes kind of live in the same space. To get started with this idea, let's scroll forward in our lecture notes to the bottom of page 9, where we introduced the existence and uniqueness of solutions. At that time, we introduced the rank of a matrix as the number of pivot columns, or the number of pivots that we see in our matrix. If the rank of the coefficient matrix, so here I'm just talking about the matrix A, so just the left side of our augmented matrix. Remember, this is your coefficient matrix. So if the rank of the coefficient matrix A, written as R of A, satisfies any of the following: if the rank of A is less than, or if the rank of A is equal to the number of the pivot columns in the RREF of A, then there is going to be one unique solution. However, if the rank of A is less than the number of columns in the RREF of A, then this is where we're going to expect to see infinite solutions to our system of equations. As we did with our first order linear differential equations, we will write our general solution as the sum of a homogeneous and a particular solution. So let's look at an example. With this system of equations, we must start by first rewriting the system as a matrix equation. So I'm asking you to write it in the form AX equals B. And we'll start by grabbing our coefficient matrix A, which would be 3, 2, negative 1, 1, 1, negative 1, times a vector of just variables, and this will equal the right-hand side of our system of equations. Now recall step 1 of our process is we want to write the augmented matrix. So recall our augmented matrix is going to be of the form A adjoined with B. After we write our augmented matrix, then we'll move on to step 2 which is use elementary row operations to write in RREF. So reduced row echelon form. So let's get started. Let's start with our augmented matrix. So to create our augmented matrix, we'll write our coefficient matrix. And again, I like writing a vertical line to separate the coefficient matrix from the right-hand side. But recall, this is a stylistic choice. Now recall, to get our matrix in RREF, we're looking for ones in these diagonal positions. And I want this value here to be a 1. And there's more than one way we could do that. We could go 1/3 times row 1, but notice that that'll create fractions with these other entries. So rather than multiplying by 1/3, which is completely appropriate, I want to use my mathematical cunningness to recognize that I can do it in an easier way if we just swapped rows 1 and row 2. So switching rows 1 and row 2 would make our matrix look like 1, 1, -1, -1, 3, 2, -1, -1. And again, this should make sense. All we're really doing is changing the order in which I wrote these two equations. There's no reason to think that the first equation has to be the first equation. Now that we have a 1 in this pivot position, we're going to use that pivot number to make what's below it turn into zeros. And so now we look at this value 3, and we say to make this 3 be a 0, we could go -3 times row 1 and pay attention to how I'm keeping track of my operations that I do. I'm writing it on the same row as the one I'm manipulating. When we do this operation, the first row does not change. So we go -3 times 1, add it to 3, we get 0. -3 times 1 is -3, added to 2 is -1. -3 times -1 is +3, minus 1 leaves 2. -3 times -1 is +3, minus 1 is 2. Keep track of of your operations you're doing. The most common mistake is to make some kind of arithmetic operation in these steps we're doing. Okay, we would now like this next pivot number to be a 1. And the easiest way to turn that pivot number into a 1 is to multiply row 2 by -1. In doing this row operation, the first row does not change. So -1 times 0 is still 0. -1 times -1 is 1. -1 times 2 is -2. And -2 again. Now that we have a 1 in this pivot position, we want to use it to make the values above it turn into 0. So I'll do that by maybe going negative row 2 plus row 1. When you're doing this row operation, the second row is not going to change. So negative times this 0 added to 1 is still 1. Negative times that 1 added to this 1 is 0. Negative times this negative 2 is positive 2, minus 1 is 1. And this also is a positive 1. We are now written in RREF form. And so let's think about our solutions now. Here we have 2 pivots, but the number of columns in the coefficient matrix is 3. Okay, we're just looking at the coefficient matrix. So we can say because the rank of A is 2, which is less than 3, we know we're going to have an infinite number of solutions. Now, to find our infinite number of solutions, we're going to rewrite our matrix as a system of equations again. And then, well, let's just stop there. Let's rewrite our system of equations. So as we rewrite our system of equations, I'll rewrite this as a matrix equation. So I'll take my augmented matrix with entries 1, 0, 1, 0, 1, negative 2. We'll reinsert our vector of variables, x, y, z. And then the right-hand side, 1, negative 2. Now, as a system of equations, this would look like x. Now, I'm multiplying my matrix times this column vector here. So when I multiply that matrix, you get 1x plus 1z equals 1, or y minus 2z equals negative 2. Now in this form, we talk about our pivots again. Our original matrix had 2 pivots. That corresponds to this variable x and this variable y. So we call x and y your pivot variables. The remaining variable, z, we refer to z as the free variable. So now what we would like to do is solve for the pivot variables in terms of the free variables. And usually what we'll do is replace our free variable with some other variable. So what I'm saying here is we'll also let z equal t. What I'll be doing is rewriting my system of equations in terms of some other variable than the one that's present. So what I'm trying to get to is we'll have x equals negative z, but I'm really going to let z equal t, so negative t plus 1. Y is going to equal, we'll move this 2z to the other side, replace z with a t, so it'd be 2t minus 2. And then z is equal to t. Now I'd like to rewrite my system of equations, or my solution, as a vector equation. The way I write it as a vector equation is we let the left-hand side be the vector x. So the vector x represents our vector of variables x, y, and z. So our vector x is going to be the sum of a homogeneous solution. This is where our homogeneous solution comes from. This is going to be where our particular solution comes from. Now, the way I write it is we'll separate the t out of the homogeneous and write it as the equation -1, 2, 1 multiplied by the variable t plus our particular solution 1, -2, and you need to have 3 components in here, so I'm going to put a 0. This is our general solution to our system of equations. What you'd like to know with this is that each value of t that we insert will produce another solution to our original system of equations. So let's explore this idea for a moment. Consider t is equal to 0. If t is equal to 0, then we get the vector x equals, well, now if t is 0, 0 times anything is 0, and so we just get 1, -2, 0 as a solution. And we can verify this as a solution to our equation. If we go back to our original system, and I'm going to erase this to try some more in a moment, but imagine if x is -1, oh, not -1, I think x, was x 1 or -1? X is 1. X is 1, y is -2. If x is 1, y is -2, and z is 0, then you have 3 minus 4 plus 0 is -1. If x is 1, y is -2, z is 0. 1 minus 2 plus 0 is -1. And so we can verify, yes, this is a solution. But let's try another one. What if t is not 0? What if t is equal to 1? If t is equal to 1, then we get the vector. Well, if t is equal to 1, then imagine there's a 1 right here. 1 times this vector is itself, and so we'll add these two vectors together, and we should get 0, 0, 1. So 0, 0, 1. This should also be a solution to our system of equations. So erase my other one we did. Now try to imagine plugging in 0 for x, 0 for y, 1 for z. This would equal -1. 0 for x, 0 for y, 1 for z. That also equals -1. So this is another solution. But again, remember, this produces solutions for every value of t. So let's try another one. If we consider t equals 2, then our vector x will look like, now if t is 2, you have 2 times -1 is -2, plus 1 is -1. If t is 2, 2 times 2 is 4, minus this 2 is 2. If t is 2, 2 times 1 is 2, plus 0 is 2. This should also be a solution. So negative 1, 2, 2. Let's go back to our original system. Let me erase this so we can try it again. And let's plug in negative 1 for x, 2 for y, 2 for z. So this would be negative 3 plus 4 is... Negative 3 plus 4 is 1. 1 minus 2 is negative 1. Negative 1 for x, 2 for y, 2 for z. So we negative 1 plus 2 is 1. 1 minus 2 is negative 1. So this one's also a solution. Okay. So notice that for different values of t, we get different solutions each time. And in general, when I look at my solution, we want to identify that this is your homogeneous solution. This is your particular solution. Okay, let's try another example. Let's solve this system of equations, but this time I'd like to do it a little bit differently than last time. I don't want to do hand calculations for all of our problems because realistic hand calculations are done only for instruction. What I would like to rather do is use technology to help us with this solution. So I'm saying let's use the calculator or other matrix calculator to perform the RREF. Now in your homework, you'll notice the notes I made in Canvas. That I say some of these you should be able to do by hand, but for the others, feel free to use technology to help you. So for some of them, I'd like you to be able to use the appropriate software. Of course, to start with this, we still need to write our augmented matrix. So maybe let's start by writing our matrix equation. 1, 1, 1, 4 on the other side. 1, negative 2, negative 1, 1. Negative 1, 2, 1, negative 1. And now we'll perform the RREF of this. So if you have a graphing calculator, grab your graphing calculator. This would be just one of the tools that you have available to you. And so I want to show you how to use the graphing calculator to perform this row reduction. If you do not have a graphing calculator, I will show you another technique next. So to enter your matrix into your calculator, you'll notice that the matrix key is located right next to this x to the negative 1 button. In my calculator, it's in blue, so I'm going to hit second, x to the negative 1 to open up my matrix menu. And the first thing I would like to do is edit a matrix. So we'll arrow over to edit, and I'm going to choose matrix A. Currently, matrix A is written as a 2 by 2, but we can change that. Let's change matrix A to be a 3 by 4. So 3 rows, 4 columns. And now let's enter in the values of our augmented matrix. So 1, 1, 1, 4. 1, negative 2, negative 1. Oh, I had a typo. I wasn't watching what I was doing. Let me start over. Second matrix, edit. make sure I got this entered right. The first row is 1, 1, 1, 4. Then it was 1, -2. Up, I'm hitting the wrong sign. I'm hitting a minus. I need to be hitting a negative. So hit the negative button on the bottom. -2. -1, 1. Then -1, 2, 1, -1. Here you want to take a minute and verify that you've entered in all of the values correctly. So I'm going to go down the columns here. 1, 1, -1, 1, -2, 2, 1, -1, 1, 4, 1, -1. I feel like I have it right. So now I'm going to quit and go back to my home screen. So second, quit. And now we're going to ask the calculator to do the row reduction for us. So go ahead and go into the matrix menu. Hit the second matrix. This time we'll do some math. And the RREF is at the bottom of your list. You could go down to the bottom one at a time, or if you want, you could just hit the up arrow. But RREF is option B. So we'll do the RREF, and now we'll tell the calculator that we're looking at matrix A. So now grab matrix A. And we get back this this row reduced matrix. Currently it's in fraction form, or sorry, decimal form. I'd rather have fractions. So I'm going to hit the math key and have it convert my answer to fractions. And so what we get back is the matrix 1, 0, 1/3, 3. Zero, 1, 2/3, 1. It keeps get rid of my calculator when I start writing. Make sure you copy this down correctly. And then there's a row of zeros along the bottom. Okay. Now that we have our reduced row echelon form, we want to identify that the rank of our matrix, the number of pivots that we have, so here the rank of our coefficient matrix is 2. But remember, there are 3 columns in the coefficient matrix. So because the rank of A is 2, which is less than 3, this tells us we're going to have an infinite number of solutions. Okay, so to find our infinite numbers of solutions, let's identify our pivots by writing our system of equations again. So as a system of equations, this would look like x plus 1/3 z is equal to 3, y plus 2/3 z is equal to 1, where we're going to say x and y are the pivot variables. These correspond to the two pivot numbers that we had. Z, that's your free variable, which I would like to introduce some other variable to represent it. So let's use T. So now let's solve for our pivots in terms of our free variable, but replace it with the letter T. So this will give us x equals negative 1/3 T plus 3. Y is equal to negative 2/3 T plus 1. Z is equal to T. Of course, I'd like you to write your answer as a matrix or as a vector equation. So let's introduce the vector x to represent the left-hand side. Now remember, this is where our homogeneous solution comes from. And then this is where our particular solution comes from. So to get our homogeneous solution, let's factor out the t, write it as negative 1/3, negative 2/3, 1 times the variable t, plus our particular solution, 310. This is what our general solution to this system of equations looks like. And again, I think it's important for us to acknowledge that when we write this, that we do know that this is your homogeneous solution, and this is your particular solution to the non-homogeneous equation. Okay, now if you don't have a graphing calculator, you'll probably want to use some other software to be able to do this, and I'll show you that in one of my next examples. So let's move ahead. For this example, let's find the general solution to this system. Now, I've already provided here the augmented matrix and the reduced row echelon matrix to save us some time from computing those. But I want to show you how to grab this RREF matrix using another technology. So to help us with that, you may want to write this matrix down, because I'm going to go back to our Canvas homepage and show you a matrix calculator that I provided for you. So take a moment to copy this matrix down if you'd like. And let's go to our Canvas homepage. On our Canvas homepage, if you scroll towards the bottom, you should see a couple of links for software. The one I want to look at is labeled Matrix Calculator. Now, there's a lot of things under this Matrix Calculator, but I want to grab the one that says Transforming a Matrix to Reduced Row Echelon Form. You'll specify the dimensions of your matrix. So ours had 3 rows, 4 columns. Or 3 rows, ours had 5 columns. And let's enter in the values of your matrix. And again, take a moment to make sure you entered those values incorrectly. It'd be terrible to proceed from here just with a typo in our entries. But verify your values are correct. I'm going to go by column. 1, 2, 3, 2, 4, 6, 2, 5, 5, 7, 16, 19, 5, 12, 13. I believe I have it correct. And I'll hit submit. And it shows me the row operations it used, but what I think is important is the very last matrix at the bottom here. So your reduced row echelon matrix is this one. So let's copy down our reduced row echelon matrix, or reduced row echelon form matrix. And let's go back to our guided notes. Okay. Notice that I've already provided you here with your reduced row echelon form matrix. So what you'd like to be able to identify from this step is which are your pivot variables. That'll correspond to this value in the matrix and this value in the matrix. So our pivot variables, I'll see this value would correspond to the x variable, and this third one in your third column would correspond to your z variable. So these are your two pivots, x and z, which would make your free variables be the ones without pivots, which would be the variable that was in this column and the variable that was in this column, which correspond to y and w. The presence of these free variables tells me I'm going to have an infinite number of solutions. Or we could have written it as the rank of A is 2, because there's 2 pivot variables. Which is less than 4, because there were 4 columns in your matrix A. So again, this would also tell us that there are an infinite number of solutions. So to find our infinite numbers of solutions, let's rewrite our matrix equation as a system of equations. So I would read this as x plus 2y plus 3z equals 1. Now typically our second variable would be y, so I'm going to put a placeholder for y in here that says y is free. Our next pivot was z. No, x, y, z. I think I wrote this wrong. This is not a z. This was supposed to be a w here. xy plus 3x plus 2y plus 3w. Because there were no z's in the first equation. But the third one is going to be z plus 2w equals 2. And then our next free variable was w, so I'm putting a placeholder here to remind me that it's free. Again, we would like to replace our free variables with some other variable. So let's let y be s and w be t. And now let's solve for our pivot variables in terms of our free variables. So we'll rewrite this now. I'm going to write it as x equals, I'll subtract the 2y to the other side, but instead of calling it y, I'll call it s. So negative 2s, subtract 3w, but w is really t, plus 1. Y was a free variable, which was s. So 1s. Z, solve for z by subtracting the 2w to the other side, but w is really t, so minus 2t plus 2. And then w, our other free variable, is just t. So I'll put a 1t. Notice how I'm keeping these in columns still. I'm lining up my variables. Because in our last step, I want to rewrite my solution as a vector equation. So we introduce the vector x to represent the left-hand side of our equation, equals. Now, because we had two free variables, we're going to have two homogeneous solutions. This is one of your homogeneous solutions. This is another one of your homogeneous solutions. So both of these represent homogeneous solutions. And this last one represents your particular solution. So if I factor out the s out of the first homogeneous solution, we'll write it as -2, 1, 0, 0, s plus, out of your second homogeneous solution, we'll factor out the t. So -3, 0, -2, 1, t, plus your particular solution, 1, 0, 2, 0. And now this will be your general solution to the system of equations. Now, one of the things that you'd like to identify when doing this problem, or now that we finished it, is that notice that we had in this problem two free variables. The presence of the two free variables, w and y, the two free variables, that's what led us to have two homogeneous solutions. So there's something to know. The number of free variables is always going to be your number of homogeneous solutions. And your homogeneous solutions always have the s and the t on them. While your particular solution does not have any variable at all. So this is your non-homogeneous solution. Okay, I think this is going to give you everything that you need for your homework in chapter 3.2. So I'm going to stop here. I will see you in our virtual class session where we can do a couple more examples and maybe answer any questions you have. But I hope this video is helpful, and I'll see you next time.